Recording. Okay, great. I think we are good to go.
Okay. Welcome everyone to the thesis defense of Murtaza Dalal. Murtaza has been with us for 5 years, was working on a lot of different areas in robotics. Has done phenomenal work that you will hear about, some of it you'll hear about today. Specifically, his whole, his PhD thesis is about unlocking generalization for robotics, modularity, and scale. Couple of things I wanted to mention before we start. So Murtaza is going to give a talk for about 40-45 minutes. If you have clarifying questions, you can ask those questions. But if you have sort of in-depth questions, let's leave it after the talk is done. The way that we typically do at CMU is we're going to start with committee asking questions. Typically, furthest away will go first. And then we pass it to the audience. And after that, we're going to have a discussion and decide whether Murtaza gets his PhD or not. So no pressure, but let's welcome.
All right. All right, so thank you so much for that introduction, Russ. And thank you guys all for coming here today. I really appreciate it. Everyone in person, as well as folks on Zoom. Thank you so much to my committee members again for agreeing to serve. And yeah, with that, let's get started. So yeah, as Russ mentioned, my PhD thesis is titled Unlocking Generalization for Robotics via Modularity and Scale. So let's begin by asking the question, what are generalist robots, and why might we want them? Well, generalist robots are broadly capable systems that can solve a wide variety of different tasks while operating in diverse scenes and environments. They allow us to operate a single hardware platform autonomously to handle whatever we want them to, potentially acting as a means of quelling the labor gap. Now, before we can tackle how to build generalist robots, let's try to first understand, what does generalization even look like in robotics? And so we're going to decompose this generalization problem into 3 rough categories. The first category is semantic or task level generalization. This category involves generalizing combinatorially over different skills, instructions, and types of commands. In this video we see here, combinatorial generalization is at play as the robot is breaking apart this task into a novel subsequence it has never seen before, and then it proceeds to solve the task. The next form of generalization we're going to consider is visual. This entails generalization over visual diversity, obstacles, and terrain. And as you can see in these videos, the robot is pretty capable along these axes. The final axis is physical, or behavior and control level generalization. This involves generalizing over different objects, poses, and even behaviors themselves. This is probably the most challenging form of generalization in robotics because it's the one that fundamentally requires the most data. And so overall, these are the 3 primary axes of generalization, which cover things like poses, scene arrangements, receptacles, objects, tasks, and so on. So now that we've defined what it means to generalize in robotics, let's look at the current paradigm for tackling generalization. And I'm sure you're very familiar with this, but it's in the machine learning community, data-driven learning has been shown to handle very complex generalization problems in both vision and language, and now many more modalities. And it has a super simple recipe. Large data sets combined with large expressive models produce broad generalization. And this paradigm has really taken the world by a storm over the last decade, becoming the dominant form of achieving broadly capable systems for a variety of vision and language tasks. So naturally, the question that you may have is, can we extend this paradigm to robotics, and how? Well, there are some issues with kind of directly deploying this sort of data-driven paradigm to robotics. In our case, we need manual human labor to collect the data. No internet-scale corpus of robot data exists already. So this can come at a significant cost. We also have an enormous number of axes to generalize over, which might be really hard to fit to and potentially require intractable amounts of data. Finally, we also have the issues of running on physical hardware, namely safety, reliability, and deployability. So, on the other hand, what have roboticists been doing all of these years? Well, again, as a lot of you roboticists in the audience might be familiar with, Nearly all successfully deployed robotic systems today are inherently modular. Take anything from factory line assembly to even a Roomba, and modularity is a central component. Why? Well, it allows us to decompose the problem into individual components, for example, sensing, planning, and acting, and each of those problems can be handled by an independent component, which allows for greater interpretability, as well as some level of performance guarantees. So what's the problem with these types of systems? Well, currently they're extremely specialized with very carefully designed hierarchies for particular problems. They often use classical planning algorithms, which are brittle because they depend on accurate pose and state estimation and sensing, which can limit in the wild deployment. So taking a step back, we've seen these two approaches for generalization. We have large-scale learning, we have modularity, and each of these have their own trade-offs. So can we unify these approaches somehow and potentially try to get towards the best of both worlds? So that's the key insight of my work, that we should use modularity to decompose the generalization problem into independent axes, which you can then solve via large-scale learning. And so in this talk, I will make the argument that modularity, along with large-scale learning, can enable us to potentially have general-purpose robots. Over the course of this talk, I'm going to outline the work that I have done over the last few years in building towards this vision, which I would say has three core components. First, I'm going to explore how modularity can be integrated into learning and can be used to accelerate and improve learning performance. Next, I'll scale learning up to produce generalization across specific axes for robot control. And then finally, we're going to put everything together into a single generalist agent for manipulation. So as a teaser, I wanted to show you this final result called ManipGen, which is a single generalist agent across manipulation tasks. It's a text conditioned agent, meaning that it takes in natural language input and acts, and it performs zero-shot long horizon manipulation. We deploy it on a diverse array of tasks with a variety of different setups. And I really want to emphasize here that these tasks are actually very difficult, a lot harder than what you would see normally because these scenes are very complex with many obstacles, objects, and receptacles. This single agent has to perform collision avoidance, generalize to arbitrary objects, and perform constrained manipulation. And again, all of this totally zero shot, no additional training data. So how did we actually get here? How did we get to this robot that's able to do all of these different things simultaneously? Well, that's going to be the focus of today's talk and basically the whole story of my PhD journey to get here. So with that, let's jump into the first part. In order to integrate modularity into learning algorithms, there's several key questions we need to consider. So first of all, how do we actually construct the hierarchy? In this work, we explore two different forms, high level and a low level split, so two-way, or a three-way high, mid, low level split. We also try to investigate what to learn versus what to plan. Here we explore learning the high level and planning through the low level control, as well as vice versa. Now, to effectively isolate and study the impact of modularity on learning, we're going to evaluate on the setting of online reinforcement learning. Because in this setup, we have no assumptions, no prior data, no additional knowledge. We're simply trying to solve the task as efficiently as possible. And in doing so, we can start to understand which paradigm is more effective or data efficient. Our goal here is to leverage modularity to maximize learning performance, enabling us to understand how to best integrate the two. So we're going to outline two key approaches, the first of which involves learning the high-level components of the task while manually specifying and planning through the low-level control. So taking a step back, we ask the question, what are the core challenges for solving a robotic manipulation task? Well, these tasks require complex interactions in the environment, making and breaking contact, moving and arranging objects into precise arrangements, multi-step reasoning. And often the task success probability can be quite low, since the probability of success of the entire task depends on a product of conditional probabilities of how well you can solve each individual subtask. So can we use modularity here to simplify the problem? Well, in the robotics community, structured action spaces, primitives, or skills have long been used to ease the control and planning problem. Dynamic movement primitives and probabilistic movement primitives are some well-known and very effective examples, but they require manually collecting human data and can be brittle when deployed. On the other hand, we have task and motion planning literature, which also uses primitives, but in many cases requires access to the true state of the world and collision checking in order to be able to operate. So instead, we're going to propose robot action primitives, or RAPs, which are a set of primitives or skills that are expressive, easy to define, task agnostic, and transferable across robots, tasks, and environments, as you see in this video. So what are RAPs? Well, RAPs are parameterized functions that execute a predetermined behavior depending on their input argument. They're basically skills such as lifting, grasping, moving forward, moving backward, etc. This is what they look like. They take in an input argument, S star, or that they take in an input argument that is used to compute a target robot state, S star, for the robot to achieve. Then the robot executes a feedback control loop to drive the robot state to S star using a primitive dependent controller and error metric. Crucially, these primitives are not dependent on the environment at all. They're just a function of the robot's proprioception. That's why they're so transferable. And so let's walk through an example. Lifting. So we pass in a delta z for how much to lift the arm. We compute the target robot state S star from that. And then the feedback controller is just an end effector controller. The error metric is just delta z. So importantly, exploring over the space of primitives leads to significantly more meaningful behavior than random actions. And so in terms of how we're going to integrate this into a reinforcement learning algorithm, given an input image, we're going to train a policy that outputs a categorical distribution over primitives and mean and variance parameters of all of the arguments of those primitives. So after sampling a primitive, which looks something like this, you're sampling from this categorical distribution. You then also sample from the mean and variance parameters by essentially selecting the appropriate ones and then just sampling from the Gaussian. Now you have an argument which you then call this primitive on when you deploy it on the robot. And so RAPS essentially replaces the lower level action space. Now, in our paper, we evaluate RAPS on a wide array of different tasks from single stage manipulation benchmarks. In this slide, I just want to really highlight that how well RAPS scales to long horizon decision making, in which you have to solve multiple subtasks. Here's some videos of what it looks like, but this is all trained from scratch on sparse rewards. So fairly challenging tasks and outperforming the baselines. So while learning the high level and planning the low level, as we've done here, is quite effective, the problem is it's limited in the type of tasks you can express, and it doesn't really take advantage of the strengths and weaknesses of planning and learning in perhaps the best way. So now we're going to explore the reverse decomposition and see how much more effectively we can integrate modularity into learning. So let's begin by discussing existing techniques for long horizon robotics tasks, which are generally more challenging. On one hand, we have the classical algorithms, which can perform long horizon reasoning quite well, but they often require access to privileged information, as I mentioned before, and they struggle with contact-rich interactions. On the other hand, we have end-to-end learning, which can acquire these very complex behaviors, and operate over raw observations, but they often struggle to explore, which makes it difficult to acquire them to begin with. And then finally, let's discuss a recent class of methods for solving long horizon robotics tasks, namely large language model-based planning, which can effectively plan zero-shot without privileged information, but they do require pre-trained skills. And so in this work, we're going to actually focus in on combining large language models with end-to-end learning as a drop-in replacement for classical planners. And we are going to try to now solve very long horizon robotics tasks. So how do we do this? How do we flexibly combine the strengths and weaknesses of these two methods? Well, ideally, we'd want LLMs to guide policies to learn online to pick up new skills and improve with data. And so the naive solution to do this would be to just have an LLM planner and a language conditioned RL policy. The problem with this approach is that you might need an enormous language conditioned data set or set of tasks to even acquire this policy. Instead, we would like to have an agent that can leverage the strengths of all the methods that I described in the previous slide to obtain an agent that can solve these challenging long horizon tasks with as few assumptions as possible. And so what we're going to do instead is we're going to use vision and motion planning to step through the language plan, learning local control policies instead using reinforcement learning. And so what motion planning is going to allow us to do is ground the language plan in the robot scene and enable the RL policy to only focus on contact-rich interaction. And so our method is called plan sequence learn. It uses a large language model to decompose a task into a coarse, high-level plan. It uses vision and motion planning to actually step through this plan. And then it uses reinforcement learning to efficiently learn local interaction. So let's walk through each of these modules. First of all, we need plans that can be interpreted by the sequencing module, a vision-based system that produces and achieves robot poses using motion planning. So we're going to have the LLM predict a target region of where to go, and we'll also introduce in stage termination conditions. Intuitively, these are exit conditions for a skill. For example, grasped, placed, opened, etc. And so we're going to structure the prompt in a standard manner so that the LLM can kind of take this in and give us the right thing out, with details regarding the task, scene, and library of stage termination conditions. Next, let's describe the sequencing module, which is going to take in the target region, global views of the scene, and depth images. And it's going to first segment the scene and project it into a point cloud. We're going to use segment anything and grounding dyno to do this. And then from this, we can actually estimate the target position of the object and use inverse kinematics to then get a target joint angles, which will then pass into a motion planner to actually achieve the target configuration near the object of interest, which if you squint here, it's basically going towards the can. So once we've put the agent close to the object of interest or the target region of interest, we're going to train RL policies for local interaction by optimizing just the task reward. No special additional reward engineering needed. And we're going to make 3 changes here to really maximize learning performance. First of all, we're going to train only a single RL agent across all the stages, enabling it to share the value function across the stages and adapt its behavior. We're going to use stage termination conditions, which prevent dithering behavior. So now we know when to move on. And then finally, we're going to only train this policy or this agent with local observations, in this case, wrist cameras, automatically giving it pose generalization. And so in terms of the results, we're able to solve a wide range of different challenging long horizon robotics tasks across 4 different benchmarks with fairly high success rates. All of these trained from scratch, no other prior information. And so one sort of example to really kind of drive home the point of how much better these results are compared to the previous method. This is the same kitchen environment from those other videos. We've improved the rendering quite a bit. But now we can do up to 10 stages. Before we were only doing 3. Trained again completely from scratch. And we're just able to solve pretty much everything that's happening in this environment, which, as you can tell, it takes a while to kind of get through everything. All right. Beyond that, we're also able to solve fairly challenging long horizon contact-rich tasks, such as nut assembly, which, as you can see here, has 4 different stages and requires careful placements to be able to place the nut on the peg. So that concludes the first part of this talk. What we have so far is great specialist learners that can accelerate learning via modularity. But what we always really wanted was generalization. And so we're going to first investigate this independently of modularity by scaling things up. Okay, so coming back to data-driven learning, for robotics, what is the core bottleneck? I'm going to argue the core bottleneck is data. We need task-relevant and diverse data, but the problem is robotics requires real-time online interaction with the real world, which makes data collection extremely difficult to scale, especially with human labor. So let's propose an alternative recipe for scaling robot learning. We can use simulation as a means of generating enormous amounts of data, essentially infinite. We can then use procedural scene generation as a way of making things as diverse as possible. And then finally, to generate expert data itself, what we're going to do is we're going to use planning algorithms, which can already solve a wide range of tasks in simulation when everything is known. And then we're going to distill them into closed loop visual motor agents that can operate in the real world. So let's begin by studying how to actually structure this data generation process and learning around a specific planner to scale up robot learning for manipulation. As an overview in this work, Optimus, we're going to generate data at scale using procedural environment generation. We're going to solve tasks using a task in motion planner, which is a classical planner for long horizon manipulation. And then we're going to filter and curate the data and fit it at scale using behavior cloning. So the first step will involve generating vast amounts of demonstrations on a diverse range of tasks with diverse sets of objects, scene arrangements, etc. And then we're going to solve these manipulation tasks, like I said before, using the task and motion planning expert. Now, the problem is that naively just fitting this data is actually not particularly effective. And so we're going to need to propose some strategies for actually processing this data so that we can maximize learning performance. And so the first problem we're going to tackle is that task and motion planner generated actions are difficult to fit to when learning visual motor policies because they're in joint space. And to do so, the agent has to essentially learn the camera projection from pixels to end effector poses and the inverse kinematics mapping from poses to joint angles. Instead, we're going to offer a very simple solution, switch to task-based control. And the key point here is that we're going to just change the demonstrations using forward kinematics into task-based. And then we're going to track them using an end effector controller and just fit to that data. The next problem is actually one that comes up whenever you want to imitate a privileged expert, because the task and motion planner operates over information that is not available to the policy, which can make it difficult for the policy, which is operating on visual information, to infer why the expert did what it did. And so there's a variety of different solutions that you could potentially use in this sort of regime. What we opt to do is essentially give the agent as much information as possible, which involves history of observations, using really well-tuned camera views in which you can see everything that's going on, and a wrist camera, which helps it observe when you're close in for contact. Finally, and this is also a pretty kind of gnarly problem for the agent to fit to, is that variance in randomized planning can produce trajectories that are far out of distribution, which can increase the likelihood of compounding error, which, as you know, is a very significant problem for behavior cloning. And so our solution is going to be to use data pruning. We'll remove outlier trajectories that have length greater than 2 standard deviations away from the mean trajectory length. And we're going to prune out trajectories where the end effector pose exits the visible workspace, reducing the likelihood that the agent will sort of fall out of the standard manifold of things that it observed in the dataset. So let's outline the actual architecture now that we use to train these policies at scale. For each time step, we're going to encode the proprioception and camera views into separate embeddings. We're then going to fuse these embeddings and project them into the embedding dimension of a transformer. And then finally, we're going to process the per time step tokens using a transformer and output a distribution over actions at the final time step, or sorry, at the next time step. And so 2 important details here to sort of remember. One, we had to use a very short context length here to ensure that the model was actually able to fit the data really well. And we found that using a Gaussian mixture model is really important as the output distribution because the data is so multimodal. Also, one thing I quickly want to highlight here, this work was actually among the earliest papers to actually explore doing transformers for behavior cloning. Things are very different these days, but this is what it looked like back then. So in terms of results, Optimus produces closed-loop reactive policies that are capable of solving over 300 long horizon manipulation tasks with up to 8 stages and 72 different objects. Again, just doing pixels all the way to control. It can learn policies capable of solving multi-stage manipulation tasks, which require the network to learn to fit a variety of different types of behaviors. It can also adapt the task planning capabilities of a task and motion planner expert. Here, it learns to clear the area in front of the microwave when it's blocked before opening the door and placing the cup inside. This is cool. This just came from the data. And so I want to also highlight the generalization results here in terms of just like the numbers. We showed that across 72 different objects, Optimus can achieve up to 75% success rate. Again, outperforming the baselines quite a bit. And that trend continues as we go to some of the other tasks. But as you may also notice, the more objects we add, the worse the performance gets. And so this is actually a pretty challenging problem for behavior cloning in general. And maybe one thing to kind of highlight here is that there will be a solution later on that we'll sort of discuss. So while Optimus achieves great results and the recipe is pretty powerful when applied to this sort of regime, it's difficult to scale this end-to-end manipulation with one network on its own due to sort of the inherent complexity of the problem. So instead, what we're going to do is we're going to try to stress test generalization by focusing in on a single skill, collision-free motion generation, but really crank up the diversity on objects, obstacles, and scene configurations. So in Neural Motion Planner, the final part of this section of the talk, we're going to aim to do exactly that. We're going to push the limits of generalization with a single skill and maximal diversity. And so I want to start by talking about the motion planning problem, which is a foundational skill for robotic manipulation. Here, I'm going to show two videos of people that are just going about their daily lives. And from the woman carefully rearranging items on the shelf to the man carefully placing items inside the microwave, both of them have to move in a very dynamic and reactive manner to adjust their behavior, and then also smoothly and accurately to ensure they're able to properly complete their task. And so this problem of producing stable, accurate, collision-avoidant motion is going to be the thing we're going to focus on. And existing motion planning approaches involve explicit algorithms that perform sampling and do tree search, or discretize the state space and then do tree search, or write down an optimization problem and solve it via some sort of gradient descent. The problem is that these approaches usually have to replan from scratch for every single new problem. They're not leveraging any past experience. They require perfect state estimation, which makes them brittle to noise in things like sensing in the real world. Finally, because they perform explicit planning with collision checking of some form, they're usually quite slow, taking minutes to plan in some cases. Let me show you what our system can do. Here, this is Neural Motion Planner in action across 5 challenging different motion planning tasks with diverse scenes, environments, and configurations. All of these are completely unseen, in which our learned motion policy performs quite well. And so neural motion planning essentially leverages the power of large-scale learning to solve motion planning tasks. Instead of replanning from scratch for every single new problem, we can reuse prior data. Instead of being brittle in the face of noise, we can use data augmentation. Instead of taking minutes to find a solution, we can find it in a second. So how do we do this? Well, going back to the recipe of scaling robot learning, the first step for scaling is diverse procedural scene generation. So we're going to sample programmatic obstacles in collision-free poses. I'll visualize these in the next slide. We're going to place real-world-like complex meshes sampled from a large-scale 3D object dataset called Objaverse inside these receptacles, on the table, around, and pretty much everywhere. We're then going to sample collision-free start and goal robot configurations to ensure a valid motion planning problem. And then finally, we're going to generate data at scale using a motion planning expert for supervision. Let's look at what the data actually looks like. I'm going to visualize each of the programmatic assets in turn. And as you may notice, there's significant size, shape, and pose diversity, which is critical for the network to generalize. Let's visualize the entire data generation pipeline now, which includes the meshes and multiple different programmatic assets, all sampled kind of all over the table. Again, you can see just like the sheer level of diversity here, which is, as I said, critical for performance. Let's also look at the overall data generation pipeline, which involves sampling challenging motion planning configurations, such as those inside obstacles. Again, this is not the only type of configurations we sample, but these are the hardest ones, so I really want to show you guys that part. We also doubled the data throughput by including the reverse trajectories from goal to start. So how do we fit this data? Well, on the observation front, a core design decision for ease of sim to real transfer was to use point clouds, which transfer readily to the real world. We encode the point cloud using PointNet++ and the proprioception using MLPs, feeding the entire thing into a sequence model, specifically an LSTM. We'll then output a Gaussian mixture model distribution over these actions which is necessary because sampling-based motion planner is extremely multimodal. This is sort of the same trick, same sort of thing that we used in Optimus as well. Then we're going to sample from this distribution to obtain the actions, which are delta joint angles. And we're going to do waypoint control. So that means that the network is going to just predict these waypoints, and then we can use any underlying joint space controller to actually achieve them. So instead of deploying these neural motion planners by just directly running this network on the robot, we're actually going to try to ensure some safety and reliability by performing test time optimization. Specifically, after constructing a multi-view point cloud from depth sensors in the real world, we're going to sample a set of full open loop trajectories from the model by rolling it out while keeping the scene point cloud fixed. We're then going to optimize for the trajectories that have the fewest total collisions in the environment. And then we're going to deploy the lowest collision trajectory on the robot in the real world. And this significantly improves the collision rate. So let's visualize the results of Neural Motion Planner on some of the most challenging tasks that we have. Here, one thing to note is that actually what we have today, so this is actually an older version of the system. Our latest version is actually about 2x faster in terms of just the runtime of the robot. And the motion is a lot smoother due to some smoothing that we incorporated. These are also newer results since the thesis proposal. We can also do closed loop reactive motion planning. Here, my co-lead Jim is attacking the robot with a sword, and it's able to dodge pretty effectively. And so this is a nice aspect of just training a closed loop policy that doesn't need to replan the entire future. Okay. In terms of the quantitative results, across 3 different tasks, we find that in the real world, our method outperforms AIT star by a significant margin with a roughly 80x speed up. It also outperforms the previous state-of-the-art neural motion planner, MPyNets, by an even wider margin. And it also outperforms Curobo, which is a GPU-based parallelized trajectory optimization method, which I would say is probably the state-of-the-art, like sampling-based, or sorry, state-of-the-art motion planner if you want to run something on a robot today. At least it was. But having built these systems, which can generalize well over individual axes, let's now turn back to building robot systems that can generalize broadly over semantic, visual, and physical axes. So the question naturally becomes, how do we do this? How do we unify modularity and large-scale learning to create a generalist robot? Well, let's start off with some motivation. So watch this video of a person opening a door, and you'll see that there's clearly 2 stages. One in which we reach a pre-contact pose, in this case, the door handle, and then there's contact-rich interaction, which actually involves turning the handle and pulling open the door. Maybe we can use this idea to decompose manipulation tasks somehow. So let's instantiate this by defining a new policy class, local policies, as policies that are initialized close to some object or region of interest, which we'll call the initial state distribution. They'll take in local observations just in the vicinity of the object or interaction point and take local actions in that region, aka relative actions. Sort of a simple mathematical way of viewing it would be something like this. These local policies actually have some really nice properties. They're invariant to absolute pose because they only care about the relative positioning of the hand and the object. They're invariant to the skill ordering, since we can use motion planning to take care of the chaining problem. And perhaps most importantly, they're invariant to the global scene configuration because they only care about the local region around some object. This makes it much, much simpler to generate data for them at scale. And so the core idea of ManipGen is that these local policies enable us to scale learning for manipulation in simulation and then transfer it to the real world in a modular structure to solve a wide variety of different tasks. So if this sounds a little bit familiar, it's because it is. If you remember a plan sequence learned from earlier in the talk, it used a hierarchical decomposition to efficiently train specialist policies for these long horizon tasks. But the core challenge now is moving from this specialist approach to a generalist approach for manipulation. And so there's basically 3 key steps. First, to perform real-world task planning, we need the agent to actually perceive the environment. This actually has a very simple solution. Instead of using a large language model, we use a visual language model. Next, for fast, reactive, real-world motion planning, we want to use a motion planner that can operate on a noisy point cloud input. Well, we just created that neural motion planner. Finally, we come to the core new piece of ManipGen. To train generalists that can solve new tasks in a zero-shot manner, we're going to need very, very robust local pre-trained skills. And so instead of training in the loop RL for a specific task, we're going to scale up learning in simulation and then transfer it sim to real. So as an overview of this work, ManipGen first uses reinforcement learning to acquire behaviors at scale in simulation, training single object experts using reinforcement learning. We're then going to distill these thousands of individual experts into a single visual motor policy per skill that's going to map wrist camera depth to low-level control. Finally, we're going to deploy these policies zero-shot in challenging environments by using the VLM to plan, neural MP to reach poses near objects, and local policies to perform manipulation. So let's get into the details. How do we actually acquire these local behaviors using reinforcement learning? Well, for the observations, we found it critical to incorporate significant amounts of privileged information in this phase, which we do by incorporating in shape information using farthest point sampling of the mesh, as well as components of the reward, which I'm going to describe next. So what does the reward itself look like? Well, it looks something like this as a general formulation for rewards for local policies, which has three components that essentially specify the behavior of the skill right here, if you're following my mouse. And the other two rewards are EE_obj and R_action, essentially constrain the motion of the policy, making it easier to transfer sim to real. And so now putting everything together, we're going to pass this privileged information and proprioceptive state information into the policy, and then we're going to train these policies using PPO at scale. So to see our local policies in action, check out these videos of pick, place, grasp handle, open, and close. And so for pick and place, we're actually going to also sample random clutter and distractor objects. So these are the clutter, the red is the target object, and we're going to encourage the agent to only interact with the target. And this massively increases the robustness of these policies when deployed. Another thing that I really want to drive home here is that due to locality, the simulation environments are actually incredibly simple. They look nothing like the real world. But if you remember from the very beginning of the talk, what we can actually achieve with these local policies is actually quite significant. Very complex, real world-like type environments. So I want to show you some of the diversity as well of the objects that we train on. So this data set is used for picking and placing skills. It's called UniDexGrasp, and it has 3,500 different objects with 115 different categories. So it has significant amounts of diversity, which helps with generalization. For articulated objects, the only part that's hard to really randomize here is the shape of the handle. The rest of it can be done programmatically. So we sampled the handle from the PartNet dataset with 2,500 different types. Okay, so now that we've acquired this behavior, we have it in the form of these RL, state-based RL policies, we need to distill all of these single task experts into a single generalist policy per skill. And so the key to doing this is using online imitation learning. Since RL policies can give us a dense feedback at any state, they're by definition queryable experts. So we can just do multitask Dagger. And so this is where the kind of key point that I mentioned during the Optimus paper kind of comes into play. So in Optimus, we tried to do large-scale behavior cloning with many different objects, and it kind of failed as we increased the number of objects. Here, we don't face any of those issues because we have the online corrections from Dagger. So that completely resolves the problem. Now, for the observations, we use wrist cameras, which are, of course, inherently local. Once the policy gets super close to the object, though, it might be difficult to tell what is happening. And so we also incorporate the first frame, which generally has a clear view of the object. We also need to communicate which object to actually interact with. So we pass in a segmentation mask of the target, which again is easy to get in the real world using grounded SAM. In terms of the actual training process, we found that for these local policies, you don't actually need an enormous model to be able to fit this data really well. So you opt for a really simple architecture that can scale really fast and efficiently, especially when you want a massive amount of data being passed through it. So we just use a ResNet 18 with a spatial softmax and an MLP decoder to then give us the delta end effector control actions, which we're then going to supervise using multitask dagger and train with mean squared error loss. So finally, let's come to deployment, in which the agent has to solve the task just given the text prompt and views of the scene. We're going to use the visual language model to come up with a plan for the scene. And then we're going to, in the way that will work is that it's going to first tag the scene with all the different objects that are present. We're going to pass that through grounded SAM. Now we know what grounded SAM thinks those objects actually are. Then we're going to pass that back into the model. And then it's going to come up with a plan in terms of the skill library using a formatting that looks something like this. We're going to deploy this plan open loop, estimating where to go using grounded SAM to segment the target object point cloud, averaging it to get a position, and sampling collision-free poses that point at the object. We're then going to alternate between neural MP and running the right local policy until the task is solved. That looks something like this. Okay, results. So let's evaluate MinipGen on 5 different diverse tasks in which it achieves very high success rates across the board. At least 60% on the hardest long horizon tasks, with up to 90% on some very challenging tasks like storing items in this cabinet. In general, our tasks are extremely difficult because they require the agent to perform a variety of different behaviors. Pick and place, articulated object manipulation, constrained tight space manipulation. And again, all of this totally zero shot. We're evaluating this on an extremely diverse object set, varying the objects to manipulate and the receptacles for every single task with pretty significant pose randomization to ensure that we're really stress testing MinipGen's generalization capabilities. I really want to note here, we did not train directly on any of the objects that we evaluate on. We decided all of the tasks afterwards. Instead, by training local manipulation at scale, MinipGen is able to generalize broadly. So let's look at a couple of the generalization results very briefly. We're able to handle very uncommon objects that are not present in our training data. For example, these pliers, which don't look anything like objects from the UniDexGraph dataset. Another one is this wire, which, like, from the perspective of the policy, just looks like a kind of thing that looks like that. Nothing like that exists in SIM. But because we've trained on so many objects, it's actually learned a kind of general picking function, which it's able to generalize quite well. We can also handle kind of unseen receptacles. So that's the thing underneath the object. But even though it's all been trained on like flat ground. So again, it's sort of learned to really focus in on the object and ignore sort of what's happening in the background because we've trained at scale. We can also perform well when manipulating somewhat deformable objects like the trash bag roll, soft toy, and paper towels. I won't say too much here because it's not doing too much deformable object manipulation, but I think it's still kind of interesting because these objects are not present in the training data. In terms of the numerical results, we show that our method beats out some very relevant baselines in terms of text condition manipulation. We include here not only the success rate per task, but also sort of the progress along the task measured as like the number of stages completed on average. We also have a ton of results in the paper as well, with comparisons in simulation, as well as additional real-world tasks against end-to-end RL, behavior cloning, task and motion planning, and other LLM-based planning methods. So with that, I want to kind of take a step back and just talk about what did we just learn? What were the most useful lessons from all of this work? Well, first, if you're going to incorporate modularity into learning methods, I will argue that you should plan the high level and learn the low level using some sort of end-to-end controller. Planning is pretty good at high level semantics, while learning can significantly improve low level control, which is often the part that's most difficult to manually engineer or acquire. I think you should incorporate learning at every single step of a modular pipeline. I think MinipGen really shows the critical usefulness of this. Modularity is super great, and we can use big models to talk to each other. They can be generalists within some specialty that then amplify when combined. Finally, I think distillation is extremely powerful. Whether it's planner into policy or RL into policy, the key point here is that we can separate behavior acquisition from visual motor learning. And that second part is actually really hard to get. This simplifies the problem significantly. And also, planners are extremely good at solving certain types of problems and generalize really well in the perfect information regime. So we can use them to collect a bunch of offline data and bootstrap learning. Now let's briefly also discuss kind of looking forward. What challenges still remain? Clearly, robotics isn't solved. So what's difficult and why? What should future research maybe focus on? So in my opinion, from the work that I've done, I still think learning closed loop, reactive, potentially dexterous control is perhaps the hardest challenge that remains. And not just on like rigid body objects, but on deformable objects, on more complex kind of like state changes, all of these things. But this is the core problem. And I think that a lot of the current literature is still operating on largely quasi-static setups. I mean, I'll be honest, I'm guilty of this as well. And I think we should try to move on beyond this. And we want to be in a regime where we're actually training policies and networks that are actually demonstrating closed-loop reactive behavior. I think this is critical for robustness and reliability. And I think the key to solving this is online learning. Our solution has been sim to real, but I think in a sort of long-term view, I believe that world modeling is the play. It's not good enough just yet, but I think in like maybe, I'm not going to give any numbers, but in a while, it'll get better. And I think that that's probably the way to go. But for the short term, I think I would encourage more research in this direction and try to really push the types of tasks that we do to be more closed loop and reactive. I also think long horizon manipulation is still really difficult. I think we've made some really nice progress in this thesis by using modularity and independent generalists, but the problem is nowhere near close to being solved. Can you still imagine a robot that tries to execute like 100 skills in a row, maybe 1,000? I can't. I think it will just fail immediately. And I think that the problem will be that like there's so much cascading error still. There's not any ways to actually handle failures over the long term and over repetitive motions. So in the long term, I think we'll need to see significantly better planning, which could come from VLMs plus reasoning. Also incorporating retrial behavior, both at a planning level and at a low-level control level. But at both points, we need a lot more sort of closing the loop. Finally, I want to also touch on a topic that I didn't really kind of talk about in my thesis, but I think is actually quite important: continual learning and improvement. I think it's a critical problem that we're going to need to solve to get to large-scale deployed robots in practice. Because in the real world, when we're actually deploying these things, there's going to be changes. There's going to be new situations, tasks, or even just objects. And your zero-shot model will not likely be able to perform. The real world is constantly changing, right? And so all of the work that I've shown so far has been just zero-shot deployment with no online improvement. And I think to get to that point, we'll need to not only have these strong priors that we're going to build via simulation or via all of these other methods, but also some level of like reinforcement learning or online learning in the real world. And I think perhaps one way of doing that would be fleet learning with batched RL, where we could essentially continuously gather new data, push it back into some learning algorithm offline, test it, and then redeploy it back out to the fleet. But I think this is another area where it's largely underexplored, but it's going to become much more relevant moving forward. So with that, kind of concludes like the technical portion of this talk. I just wanted to also kind of briefly talk a little bit about some acknowledgements. So first of all, I want to say thanks to all of my wonderful collaborators over all of these years. Literally, it would not be possible to do any of this work without all of these people in their environment and their involvement, whether it was mentorship or literally just working boots on the ground. Especially want to highlight my sort of co-authors, Jim and Min, without whom my last year of work, I don't think would literally be possible. You guys honestly made it happen. And so it was a pleasure working with you too. Thank you so much. I also really want to acknowledge the people in my life that kind of got me to this point. I don't think I would be here, especially without my family members, especially my parents. You guys literally have been around, my entire life for obvious reasons. And but yeah, I mean, you guys have always supported me. You guys have always kind of been there and pushed me to sort of get out of my limits and really go as far as I can. And yeah, without you, I would literally not be here today. So definitely want to say thank you to you too. And also to my uncle and aunt who are here today, who took time out of their busy schedules to kind of drop in and come see my talk. Thank you so much. And beyond my family members, there's been a lot of folks that have been involved over the course of my PhD. First of all, my advisor, Ruslan, without whom, again, I would not be here today. Thank you so much for taking me on. And it's been an absolute pleasure working with you all of these years. And all of my lab mates in Rust Lab, as we like to call it. It's been awesome. This ride has been really fun. And yeah, same thing with Deepak. Again, you've not been my sort of like formal advisor, but I've always considered you like co-advisor in all but name. And again, it's been an absolute pleasure working with you. I think you've taught me so much about some of the skills that I need to kind of get to this level, to hone my research taste and really think about the problems I need. And you've also created an extremely vibrant community of folks. I hope most of us are in this picture. And also that I've counted as lifelong friends. And speaking of friends, also want to just acknowledge all of my friends that have been around for all these years, my high school friends who've also always supported me, college folks, especially Russell, who has literally been with me since first year of undergrad, and now we'll also be working together after PhD. So kind of crazy. That's like 8+ years. And beyond that, all of my friends. I also wanted to acknowledge the weekly novelty dinner, which has been the literal highlight of my PhDs, kept me going. I think we've done like 50 or 60 at this point. It's just every Wednesday or Thursday. Absolutely love it. And then, more friends and people that, the community really kind of keeps you going through this whole thing. And yeah, just kind of thank you all for being there and with me. And yeah, if people are not shown here, I'm sorry, there's too many pictures, but yeah, you guys are all in my heart. Thank you so much.
Oh, so let's start with committee members.
Sounds good.
Asking questions, and then we'll go. So we will probably start with the person who furthest away. So maybe we can start with Shuan.
Okay, great. Thank you. Thank you for the great talk. I have seen most of the work before, but still I feel very impressed, especially the new results that I haven't seen last time.
Thank you.
Yeah. So I don't have a lot of questions, but I have two. Like one is a clarification question. One is a little bit high level question. So clarification question is that in your neural motion planning paper, in the demos that you show, do you have another message or module that determines where your end effector, the target end effector poses? Or like
so yeah, let me clarify how the experimental process worked for neural motion planner. So in these environments, like for example, these videos here, the whole point of the experimental evaluations for this paper was just checking motion planning performance. So we actually just manually generated the joint angle configurations for the start and the goal, and we just tried to make them as difficult as possible. We actually have like a pretty thorough experimental process that's described in the paper as well for like how we picked these poses, but it was all manually chosen here. And so we just moved the robot using the control mode on the Franca, and then we just have the target joint angles, and we pass those target joint angles, not end effector poses, into the, and then it achieves those. But when we deploy it in like say ManipGen, for example, there everything is automated. But here the experiments are manually designed.
Okay, yeah, I think that makes sense. And then also for this work, when you train the motion planner, do you train it with object holding on the gripper?
Yes, great question. Yeah, so I didn't actually mention that, but in the training data, we not only have object like freehand motion planning, but we also randomly sample objects in hand, which I think are max size of about 30 centimeters or so. But yeah, that's critical again for like and it's incorporated as part of the robot point cloud rather than the object point cloud.
Makes sense. Cool. Yeah. I was thinking that otherwise it won't work when you're holding books and stuff.
Yeah, exactly. We had the same thought. That's why we added that in.
Nice. Okay. Yeah. So that's the clarification question. And another question is a little bit more high level. So your thesis is about modularity. And then I guess the first question is about how to divide a big robot system into modules. You showed a few examples of how you define the modules, high level, low level. Do you see that eventually we will converge into one ways of defining different robot modules? or in your experience, you realize that from time to time, you kind of need to change the definition of module, which you actually
that's actually a really fascinating question and something that I have thought about before. I think that in at least in my work so far, I mean, you probably noticed this in terms of the types of tasks where we've encountered, they're all largely similar in terms of like how they operate. They're all quasi-static rigid body manipulation. So there, I think that like the type of modularity that I showed is probably pretty good at it. And it was kind of inspired by work in like kind of how classical roboticists already approach the problem. I think that there might not be like an optimal sort of modularity or modular sort of decomposition for all tasks that we have, simply because that is extremely broad in terms of like what are the different ways in which you can think about and approach problems, especially if you're not looking at just, you know, sort of like robots that are manipulating the world, but if you think about like maybe beyond even the types of things we've been considering here, like, you know, ocean robots, space robots, all these other things, where like the sort of modularity might just be completely different and completely independent. So that being said, though, I think like we can, and I'm not saying again that like the type of structures that I've proposed in this work are necessarily the optimal way to go, just perhaps one way that was very effective. I think that for the like humanoid type or like maybe like manipulation type tasks that we're going to be, that a lot of us are looking at these days, we will likely converge to something, maybe even something that's like slightly inspired by the sort of like cortices that we have in the brain as a way of kind of like decomposing and having these components talk to each other. I don't know exactly like what that perfect formulation will be. I hope that we can figure that out. I do have ideas on like different other ways of doing it, but I think like that part is something that we still need to figure out. And there's probably a lot of work there to do that.
Yeah, I was just keep thinking that it would be nice if we eventually converge into like one type of way of doing.
So I think a lot of folks are of the opinion that like the maybe the simplest / most general version would be like something like what Seiken does, right? Where like you just have like LLM output like some natural language command, and then you have a language condition policy. That is something that could probably be pretty broad. But I think that like it's often kind of difficult because of this. It's difficult to bridge the gap between language and control, and like training language condition policy is just practically very, very challenging. And so I see that as one potential answer to this question. But I'm almost like not convinced that it will necessarily work. There's also other aspects of the modularity question that we haven't really touched on here, which is like how do we actually layer like control? Like, for example, you could imagine like right now, all we do is we have the policy output some control in some, you know, action space. And then the lower level controller is always PID or is often PID, right? But we could have like more advanced controllers even operating there. And maybe those need to be better than kind of like the ones that we're using right now. And that may enable us to sort of shift the burden accordingly. And so what I mean by this is often that like you can separate like the maybe the more semantic and higher level components past of the task to learning, and like some of the actual control behavior, you can perhaps decompose that out and use better approaches. For example, things like geometric fabrics that have been proposed by NVIDIA as the lower level, like much more advanced controller for actually reaching poses and giving us a lot of nice properties underneath. But so again, I think like the answer here is unfortunately not very satisfying. I think I have a lot of ideas and thoughts here. But yeah, I think we still need to kind of figure this out. And maybe if more people investigate, we can get there.
Yeah. I think this is just like a very high level question because I feel it's a little bit conflicting. On the one hand, if we look at any way of doing this modularization, we can always point out limitations and issues. However, on the other hand, if we keep changing the way that we are like defining modules, it's very hard to keep reusing the modules that we developed. So yeah, so this is something that's in my mind. That's why I asked you. I don't think there's a good answer for it yet, but I like your answer.
Yeah, thank you.
Yeah, so I think that's my questions, and I will pass down.
Thank you. So maybe the next call we can pass the torch to Ankar. I don't know if you can hear me.
We can hear you, Ankur.
Can you hear me all okay now? I think
Oh, yes. Yeah. The audio's working great. Yeah.
the internet suspiciously got disconnected right in time.
Oh no.
Yeah, I think pretty good talk. Let me just switch on my camera as well. I'm certainly very intrigued by how all of this sort of culminated into ManipGen. I think it's one of the coolest papers of the year, past year.
Thank you. That means a lot.
Obviously, there are a lot of challenges involved in that. One of them, which you have been able to sidestep here by using point clouds. So the sim to real gap is significantly reduced,
Yes.
right? And I wonder, obviously, that is very constrained in some settings where you can just use point cloud only and not care about, RGB. So how do you foresee those challenges sort of affecting the performance of the system overall if you were to do that with RGB?
Okay, yeah. I mean, I think this is actually something that yeah, it's a bit challenging to address right
Yeah.
now. So small clarification there. Actually, we're using depth images for the local policies and then point clouds for the neural motion planner. But yeah, same problem remains, which is that we're using depth, right? Or in both ways. And the problem really with depth is perhaps not that present in like a lot of the tasks that we are using right now, but I think would be a problem kind of more broadly in the future, is if your decision making actually depends on knowing more than just the geometry of the world. For example, you need to know the texture and the things so that you know what object you're actually looking at, right? Because if you sort of turn off color and you just see how far things are, you don't actually know what you're looking at in the world. So those are the types of setups in which we would probably want RGB. And so that's maybe the first thing to kind of consider, like why we'd even want to do this. Why isn't depth just good enough? Obviously, we're still struggling to even get depth to the point where like it'll solve everything. So I think there's still a means to go just in that. So there's plenty to investigate there. For RGB, I mean, I think the sort of solution there, I think is perhaps a slight bit of a cop-out answer, is that we just hope that photorealistic rendering becomes better and faster, which I think it does seem like, new technologies are capable of making that better. I think that because we only need RGB in the distillation phase, though, it is a lot easier to scale, right? Because the data efficiency of the distillation phase is significantly more than than that of the RL phase. So as long as we can keep training the RL policies without RGB, then we might actually still be okay. For example, in ManipGen, let me just give a quick napkin math of like the numbers. Roughly the amount of data used in let me just pull them up as well, because I wrote this down. The amount of data that we required in order to actually train the system was about 30 billion trajectories. Okay, that's an enormous number, much bigger than what pretty much all other work does. But most of that was concentrated in reinforcement learning because it has to learn from scratch and acquire all of this behavior. The distillation phase actually doesn't have that much. So maybe we can actually get by with even slower photorealistic rendering and use that just on the visual motor learning side. And so this is actually the key advantage of this like phase 1, phase 2 approach. And so I think we might be okay with just that, at least in sort of a temporary regime. Obviously, we need to still investigate if that is good enough, because the problem once you incorporate in RGB is that the realism really matters, right? Like everything that we were doing in ManipGen, we were actually kind of also able to get away with because of the fact that it was depth. And so it didn't need to match the textures of the real world. But those are just things you need to consider in your procedural scene generation now, on top of the fact that now you have slower photorealistic rendering. So these are just things to consider, but I think if you kind of keep those in mind, and you keep generating these kind of like very diverse worlds and scenes and environments, I think it should be possible. Like, I think at least for the types of tasks we're already doing, like if the bottleneck is just like we want to like move to RGB, I think for tasks that are already solvable with sim to real with enough and correct engineering effort, it should be doable.
Yeah, makes sense. One other thing I also want to revisit is the the manual tuning required for the rewards to solve. Do you foresee yourself sort of leveraging internet data or some other demonstration-based, methodology to improve that? So, I mean, obviously, in the tasks you did, you had to do that manually, all the tuning and come up with
Yes,
the
yes.
different
This is
functions. So that's sort of the dirty thing that you had to go through. What sort of future versions of ManipGen do you envision that sort of alleviate these?
Yep. This is
these
a completely valid question, and I think this is the dirty little secret of all sort of sim to real RL papers, is that the reward tuning is kind of critical in order for everything to work. And the reward functions often look kind of hairy. They don't look very intuitive, at least at a first glance, in terms of like, and it often takes a lot of work to get there. So completely valid point, and it is a definite problem for this area. I think that there's a number of different ways in which we can try to get around this. So one thing I've observed in the literature has been, Eureka, or like using large language models to essentially generate reward functions on the fly. Now, I think the jury's still out on whether or not that stuff is actually good, namely because it's not clear that they're innovating that much in the reward function space just yet. But I think that like, okay, so one sort of futuristic version of thinking about how that would work that I think would be actually kind of exciting would be that like, okay, how does a human sort of tune the reward functions? Well, what they do is that they write a reward function based on some intuition, then they train RL policy, they watch what it does, at least the video of it, then they update the reward function. So I think that once we're at the point where we can use video LLMs, which again might be a few years away at least, once they can process that, that might be one way of actually doing this much, much better, because the feedback signal from being able to visually see what's going to happen will probably make your reward engineering significantly better, right? Because I cannot imagine, like, by just looking at the reward traces, being able to truly come up with a new and useful reward function, because you don't really understand, you don't have good intuition for what's happening. But by looking at the video, you can actually do it. And you can even take that a step further and then deploy it on the robot. Again, pass that video back into the video LLM and have it continuously improve. But I think at least the first way in which you just look at the video in sim is very, very scalable, and could potentially be one way in which we actually automate this reward function generation process completely. The other way I see of being able to handle this is actually by leveraging some sort of either internet scale, maybe human video data, or by leveraging the massive corpus of real world human labor collected teleop data that people are using. So right now, every single person is just using that for behavior cloning. But I actually think there's a lot of other useful things that data can sort of give you that people are just not looking at right now. And I think one of those is reward learning, right? You can just take that data, you have optimal trajectories, you can use that to actually just train classifiers for the type of task that you want, and you already have success trajectories, so you may as well just do that. And then we can potentially, if we can find ways of throwing that back into simulator or maybe into a world model, which is potentially also handling this kind of like realistic rendering for you, we could potentially use these reward functions as a means of getting the behavior that we want. And I think a similar case can be made for human video, where we can actually take the internet scale, maybe something like YouTube, extract out, what's happening in the world, and maybe use that to build like reward functions for robots again. But yeah, those are some thoughts at least.
No, that makes total sense. One fun question: if 10 years from now a new Murtaza comes in and wants to work with Russ on ManipGen again, what sort of changes would you add to it to make it work for, say, 1,000 tasks?
Ooh. That's a great question. So actually, first of all, I would say that like if I was gonna sort of work on this, maybe, well, I don't know. Is robotics going to be a hard problem 10 years from now? We don't know. But okay, aside from that being a sort of a question, I actually think that like the part that we didn't really tackle here was, or like there's a lot of things we didn't tackle, but I think like that would be quite interesting to sort of focus on here would be to extend this to like actually maybe like much more complex robot morphologies. I think that that's like kind of where we really can get the biggest bang for the buck. So I think like and that would be something that would be like much harder than what we have right now, and potentially unlock a much larger array of tasks. So I would probably want to focus on, okay, this is going to sound cliche because everyone's doing this these days, but probably humanoids or something of that sort, like something much more dexterous, much more mobile. And then it would kind of make the problem a lot more complex, because now you probably also need to do mobile manipulation. You need to be able to do dexterous manipulation. And then you also want to maybe focus on things like, beyond rigid object manipulation. And there, I think actually ManipGen in a slightly different form could potentially be practical for things that we cannot simulate. And the key idea is very simple. I actually did not have time to work on this in my PhD, but did consider it, was you can basically just do local behavior cloning of the same sort, combine it with the modular pipeline that we already have, and now you can probably also solve a lot of different tasks that just simply cannot be simulated. So that's a free paper idea if anyone wants to take it. I think it's actually quite easy to implement, but yeah, anyways, that's my answer for that. Yeah.
Okay, all my questions done. Yeah.
All right.
Thank you.
Yeah, great talk. Really interesting work.
Thank you.
So we'll start with something maybe somewhat technical. So you have this idea, which many papers do as well, which is to train a policy with RL using privileged information and then distill it into a policy condition observations. And one problem with that approach is that the distilled policy only has partial observations, so the optimal action won't actually be the same action that the privilege, right? So I'll give an example. If a wrist camera, say on the grasp this object, and I'm looking over here, so I don't see the object. So the policy knows go like this. The policy that only has a wrist camera needs to search. And if it looks up and it doesn't see it, it needs to look somewhere else until it finds it, right? So, yeah, understand my point.
Yes, yeah, and I have thought about this, yeah. So that's a fair point. I mean, I think that part of the reason that we actually don't have this problem here is because we almost like explicitly like set up the problem in a way where that doesn't happen. And so what I mean by that is that we always ensure, and so this is actually just a small detail in the paper, but it kind of directly answers this question. We always ensure that the data coming from this stage is always has the wrist camera in view, or sorry, has the object in view from the wrist camera. So that ensures that when we're training, we don't actually have this problem. Now, does that mean we can acquire this behavior at all? No. And in general, I think that is a fundamental problem of distillation-based approaches, where let's say your strategy has to be completely different for your sort of visual motor learner versus the privileged learner. That is a difficult problem. I think I don't have like a strong answer for how exactly to get around that just yet. I mean, obviously there's like the simple answer, which is that we just don't do this and we just train like, one phase everything. Practically, that is very, very difficult for just mostly engineering details, but also because multitask RL is very, very difficult. Like the other thing that we get from this is that this is all single task RL, and then this is multitask imitation. And multitask imitation just works much, much better. I think in the long run, maybe if we could get visual motor multitask RL to work well and somehow also sidestep these challenges, that could work. But I think it's just like not practical these days. Like it is very, very difficult to get multitask RL to just work on any number of even problems. Like even like 5 to 10 tasks, if we try to train them all with a single RL agent, it's just not going to work very well. And I think part of that is just in like the conflicting reward gradients between the all of these different approaches. So yeah, I mean, part of it is just that like I think beyond sort of the advantages of separating behavior acquisition from visual motor learning is just the multitask part is really, really difficult to get around. And I just don't have like a good answer for how to get around that just yet. I haven't seen anything in the literature either that's saying that like, okay, we can just do it. Yeah, I think like we should try to investigate this. I think like, but I think like there's a lot of tasks that we can do in which this is just not a problem. Like, I don't think like a lot of the tasks that like we're at least trying to solve right now, that this is actually a serious problem, especially if your high level planning is quite good. Like that actually will also get you around this, because if the high level planner knows to just point you at the object, then it's never a problem, right? Because you're just going to have it in view. And then it's going to do the right thing once it's conditioned on the starting state being good, right? So that also kind of gets around this. So this is also like a question of how you push the burden of like what to do to what part of the system, right? So you sort of push a lot of the sort of you have the high level aspect of things like be better in terms of like being aware of what are the limitations of some of the lower level parts, and then maybe that will also make it feasible. I mean, again, this is just like one example where you have to search. I think it's actually quite difficult though to come up with these types of examples where it actually matters that you can see things.
Yeah.
Uh,
That's interesting. So
yeah.
So
Yeah.
the high level, that's the VLM, right?
Yes, yes.
And so what the VLM needs to do is kind of initialize your wrist camera.
Yeah.
as part of the object that you'll have to interact with, where
Yeah, which I think is actually kind of reasonable, right? Because like that is more of a semantic thing rather than a control thing, right?
Right. How does the VLM kind of identify like what part of the object? Like if it's a handle, you say go near that handle. But if it's an object that has, it's not called handle, but some other object part with the VLM kind of like.
So I think existing VLM is probably not very good, but you could imagine that like as these models get better and better at sort of like physical reasoning and intuition, like, and if you prompt it well enough, it should be able to sort of highlight these things for you. Like I think at this point, given just the evidence of like what we've seen about how good these models are getting, it doesn't seem that surprising that maybe in like 5 to 10, not 5 to 10 years, maybe in some amount of time, like we could, I refuse to give numbers because the progress in this field is just crazy. This could happen. And like, I think that because these high level parts are becoming smarter and smarter, we may not have to have so much burden on the low level control. And that allows us to really focus on maybe some of the parts that we as roboticists believe are really difficult, which are like actual interaction.
Yeah, I think this is sort of the big question, right? Like, I guess you're sort of saying, well, VLMs are getting better and better, so we can use them. And then other people are saying, well, imitation learning is getting better and better, so we don't need any of this. And it's a question of like, well, where are both sides going to actually plateau? And where do we fill the gaps? Like we don't, but okay, so I guess jumping to other questions. Neural MP.
Thank you.
Why is it that you outperform previous methods? Is it the data? Is it your architecture?
Yeah, great question. Okay, so let's look at like maybe what some of the prior approaches were and like why our thing might do better. So I guess it's perhaps maybe you're first wondering why is it doing better than the expert AIT star? That might be the first question on your mind. There's a couple of reasons for this. So first of all, when you deploy these like sampling-based motion planners in the real world, it's actually quite challenging to be able to do so because they still require collision checking. And the thing is that in the real world, collision checking is very noisy, and they're very dependent on this collision checking to be exact. And so there can often be induced failures because of the noisiness of point cloud and sensing. Our method, by contrast, is actually not dependent on perfect collision checking. Like we still use collision checking, but almost just as a refinement part. At the very end, our trajectories are already pretty reasonably good.
So in simulation, you would not outperform.
I think we would probably, well, okay, so there's a second point to this, which is an empirical observation. I didn't really talk about it here, but it's something I noticed in both this and in Optimus, where in both of those we're doing planar distillation. Actually, there is a table in the Optimus paper that also covers this point, which I'm about to make, which is that we noticed that if you distill like a sort of imperfect planar, because even this thing is not perfect in sim, like it doesn't solve everything. If you distill an imperfect planar into a policy and you're just taking all the successful trajectories and fitting a model to it, it actually does better than the original thing. And I think part of that is because it's seeing all of these success cases across all of these different diverse environments. And once you've kind of scaled things up sufficiently, it's almost learned like a general function that's very powerful. And that reusing of prior data and experience is something that the other approaches just do not do. And that might be why. This is just a hypothesis. We didn't really investigate this in detail, but this is something I observed in both works. So I suspect it might actually do better than AIT star even in sim. Yeah.
And then compared to like MPinets or whatever.
Well, so MPinets, the problem there is data. Like their data generation was not nearly as good as ours. They also don't have a multimodal model.
If we just took their model, trained on your data, it would be.
I think we have results with that. I think it's not as good as ours. So there is architecture also improvement with the sequence model and the Gaussian mixture model as well. But I would say definitely the core part of it is like there's a massive gap in terms of the types of data that we're generating here, which was really a core focus of this paper. Yeah.
I guess maybe just the last question is
Mhm.
why LSTM for this? LCM is interested in the history, but
Mhm.
it's sort of a Markovian task. So what do you need history?
That's a great question. So actually we use a very short history here. But it was paradoxical because I was also surprised by this. I did ablate this like very early on in our experiments. LSTM outperformed MLP, but also like increasing the history of the LSTM beyond a certain point, actually beyond just 2, caused performance to drop too. So it was like 2 was actually the optimal, which is like barely using anything. I suspect it might just be like some sort of velocity estimate that's helping it to sort of know what to do here. But yeah, it is necessary, like for performance reasons, this will do better than like the other approaches I just mentioned. But you also don't need a ton of history here. Yeah. Also, the point cloud is not perfectly observed in the real world, so it does help there too, right? Because it's partial.
Maybe it's the
Yeah.
history of the
Oh yeah, we do have history of the point clouds, right? Because it's multiple of these entire like states. Yeah.
Which part do you get a history of or something? Like,
Yeah, but I think since it's all fused into one thing. Yeah.
you have to
Yeah.
choose architecture.
Yeah. Yeah, so I suspect this, I mean, this could be important. I'm not sure entirely because getting these two, maybe you get a velocity estimate from just having 2 joint angles, which is nice as well. I mean, certainly this doesn't matter. So it's just between this, yeah, and this. Yeah. All right, thank you.
Thank you. And then maybe Deepak, you want to go?
Yes, I just show my face because I'm in transit, but then I
No
will
problem.
go video just in case. Great talk, Murtaza. I just want to say that it has been a privilege working with you the last 4.5 years. Although you
Thank
were
you so
advised, you hear me? Yeah, although you were advised by Russ, I think you have been a core member of our lab, and I'm a student. I will, get great working with you. I only have one question
Mhm.
since we have already have had years of discussion about every piece of it. So, which is on the final takeaway,
Yeah.
which you said the takeaway is plan at high level,
Mhm.
learn at low level.
Mhm.
This is for quasi-static, maybe scenarios where like things are not moving too much between your actions. What about dynamic
Mhm.
scenarios? Think of maybe, I don't know, humanoids or even like any robot which is operating in a very dynamic scenario with where it will react very fast.
Yeah,
Now,
so I think
if you think
that's a
from
fair question. Yeah.
yeah,
Mhm.
like does this framework still apply there? And what, because humans do use planning, but that's very high level. Like if you ask me a math question or something, or if you ask me the wrong terms, like very high level reasoning I would use. But as far as the body control is concerned, I don't think like after first 4 or 5 years you use planning at all in like body control of the system. So like
Yeah,
what
I mean,
on the
I see
dynamic
your
side, yeah.
point. And I guess to be fair, if you look at ManipGen at least, right, the planning is very high level. And I think that's kind of generally what I believe too, which is that like the sort of semantics and like kind of high level decision making of like, okay, what are you going to do? What sort of skills you're going to execute? I think that level should still be planned. And then
So
everything below that can still be low level.
so
Like if you
but
look
my
at
question is like, is this an eventual takeaway or is this like a step, a milestone towards a longer goal where this like a planning is using right now, we're using right now because the reasoning is not that good at longer scales, but maybe or in few years it will get better. Like, or do you think that is the framework we should take and run with it today?
Well, I think so. The reason I even say to separate these two is because I think it's going to be difficult to get a model that does both all in one, like for all things simultaneously, just simply because like I think combining the planning part and the low level control is just like 2 very disparate problems that often don't really inform each other completely. I mean, to some degree you do, of course. So I think separating them is first of all important. I think my view is that this high level part is exactly the way that you mentioned, that it should be very, very high level, like just, abstract semantics. And that's exactly the way I've kind of practically implemented it as well. I think all the rest of it, like even the motion planning in like ManipGen, for example, is a closed loop reactive policy. So the rest of it could, in theory, once it becomes much better, just be handling the dynamic reactive tasks. So I think in some sense, I feel like this does handle all of the scenarios that you are mentioning, because I think the planning I'm talking about in this sort of argument is the very highest level part of it, where it's like largely just abstract and morally like mostly just deciding like what to do and what skills to execute,
Yeah, got it. So this was high level question, and one low level question. How would you combine the low level RL policy with neural MP?
Oh, into like one policy? So that
no, I don't know one, but something more closely connected, not like two modules.
That's interesting.
Which could have been a project if you were here longer.
I mean, okay. So part of the question actually that you need to first ask yourself is like, do you even want to do that? Because the issue with doing that is that then the sort of manipulation policies will become like non-local, right? By definition. Because now they're kind of going all the way to the interaction point and interacting, which then we lose a lot of the benefits of actually kind of separating the two. But I guess if we do actually want to combine them, I mean, I think one thing.
Of course, I mean like in a way that retains the benefit.
That's actually, I don't know. I'm not sure if that is necessarily possible. I can try to kind of speculate on exactly how that could be done. So you want to have sort of the benefits of both like the sort of locality that we're getting via the simulation.
But maybe also, I'm trying to tie it to like maybe like I'll nudge you in that different direction. Like maybe I'm trying to tie it to more like hierarchical RL, which was always promised but never delivered. Maybe it's the way towards that.
Oh, where you're saying sort of that
because instead of explicit hierarchy, like there you can see like all this feudal RL and all these frameworks where you can find connections of each of these components to that framework.
But this is like
more
much
like
more
end-to-end
formed one, right? Like where you kind of like saying, okay, we have this like motion planning and we have this local control thing, which is like very different from the way that those works were doing it, where it's just generally like, oh, you have a goal and then you sort of have like a local controller to actually achieve it. Which actually you can think of as the motion.
I mean, they are from different literatures altogether, right? But I don't know. I'm just thinking along with you. That could be one direction. But I think that's all my questions. I think we have gone way over time as well.
All right. Yeah.
So hand it over to us.
Okay.
Some questions, 3 questions from the audience. Questions from the audience.
Can I ask a question on Zoom, or is it?
Yeah. Go for it. Yeah.
Yeah. Thanks. This is great talk. So I think a lot of the work is actually trying to learn generalizable policies by using simulation to generate a lot of data offline and distill them to a visual model policy and transfer that to the real world. But I think like there are certain skills or policies we just cannot learn using this paradigm by simple transfer. For example, many dexterous tasks are just not simulatable. For example, imagine you are trying to pick up the noodles from a noodle soup. That thing itself is very hard to simulate. So, and also for many other different boards. So I'm wondering, like, what's your opinion of applying this paradigm towards those kind of like more difficult tasks?
Yep. Great question. I think the answer is actually probably in the very long term world modeling. So I think that, okay, so here's my view as to why, like, so the current sort of approach and the way that people are thinking about this is, let's just do large scale imitation learning. Let's just collect the data manually and, try to just, kind of brute force our way to a policy that will work. But there's like a number of different issues with that sort of approach. One being that behavior cloning fundamentally has compounding error, and it's really hard to get around that no matter how much data that you collect offline using teleoperation, right? Secondly, beyond that, there may be certain behaviors that are just simply impossible or like very, very difficult to teleoperate because there's two there's the latency of the human reaction time and the latency of the actual teleoperation system, which might make it so that you cannot even express those behaviors. For example, a humanoid using, let's say, chopsticks, right? It is extremely difficult because it will require highly precise closed loop reactive control on the teleoperation front to even collect the data. So that means that perhaps for these types of tasks, it may even be very, very difficult to ever get the data in of itself. So then we have to think, okay, how else could we possibly get that data? And you're right that sim to real is probably not the way to do it right now because we just cannot simulate those. And that's because they're manually engineered simulators. But the reason I say world modeling as like a much more longer term view here is because the bet is on supervised learning. And I think that if we ever look at like sort of the world and what's happening right now, supervised learning is a pretty good framework to actually put your money on because it has pretty strong guarantees. We know how to kind of do it. We just need to kind of get more data. We just need to scale it up. And I could imagine that in the future, we end up just simply training everything inside learned simulators and then just directly transfer those to the real world. Now, how exactly that will practically manifest, there's of course many different challenges there too. But perhaps that's like the optimistic view of like what I think might be the way to get towards that problem. And why I also think like some of the existing approaches and the way we're looking at it right now may not be able to get there.
Okay, thanks so much. It's very helpful.
Okay, so maybe given that we kind of like running a little bit behind, so maybe we should let everybody leave. We can get to that overall. Next time we'll discuss.
Sounds good.
Yes.
So I should turn off the recording now, or?
Turn off the recording.
Okay.
I think that we should also everybody on Zoom should